Welcome to the live session. In the last live class, I discussed with you about various possible positions to place the object on the principal axis, right? So here, simply we have various positions because here we know 2 points. We know 2 points from the lens. So here we are decided that point size here focus and center. So morning one question I got in the comment section, why we are recognizing this C2 and F2 on opposite sides for different lenses. So simple to answer this question actually based on the surfaces, just I'll move on to the whiteboard here. Very easy to understand about that one. Here, suppose if you take a double concave lens, so simply it has two curved surfaces. One is, both are convex surfaces only. Suppose here, if I extend them, so it can form the part of that surface is like this. So here spherical surface actually we are imagining. For left surface, we can imagine the surface is like this. So any concave lens or convex lens, both are formed from the sphere. So this is the spherical shape actually. So here left part having the center towards right side, and right part it's centered towards the left side. Always we are targeting the light from left end to the right end, right? So here when I target the light from left end to the right end, here what is the first surface for me? So this left surface is actually first surface for me. So where is its center? For the first surface, center is actually located at right side. So that's why I am giving the number for the center is C1. Then second surface is having its center left side. So that's why it is given as C2. So this is about identifying the center of curvatures for the convex lens. So simply we'll go for the double concave lens. So here double concave lens, its shape is like this as you see on the screen. So I have the shape for the concave. Then extending these surfaces, if I extend, then it's a surface, then it is appeared as a part of sphere. Then left side surface, so you can extend it, so it's a spherical shape is observed like this, right? So here simply their centers towards left side and right side. So here simply light ray targeted onto the surface from left end to right end like this. So here first surface is left side and its center is also left side. So that's why it is given as C1. Then second surface center is right side. This is second surface. This is first surface. So first surface has its center is towards left side. Second surface center is towards right side. So that's why I'm giving this number as C2. So if you see this lens eyes like this, then you can understand easily why it is left side, why it is right side, oppositely for different lenses, concave and convex. So this is the reason to identify that surfaces centers as C1 and C2 according to the lens. So it is very easy. Then we will go for our discussion. Various possible positions discussion is over. Then the next topic we are discussing in this about the ray diagrams. Very first we will discuss about the convex lens. For the convex lens or for the concave lens, we have both 6 positions. But in the mirrors, for a concave mirror only we have 6 positions, but convex mirror we have only 2 positions. One is in front of the mirror and the other is at infinity distance. Only 2 possible positions, right? Or fixed position we will give in between pole and the infinity for the convex mirror. But in the lenses, for convex lens and for concave lens, we have 6 various positions. They are here as we discussed in the previous class. They are what? Simply between pole and the focus, at focus, between focus and the center, at center, beyond the center, and at infinity. Right? So they are the possible. So we will come from very far distance outside the center of curvature. We can name it as at infinity. So the very first position is object placed at infinity. So when the object is placed at infinity, how to get the characteristics of the image and how to show the formation of image in the ray diagram. So that we are showing in this diagrams. So they are called as here ray diagrams. So simply here we can go for the ray diagram by simple logics as we learned in the morning class. So very first you can draw a line on the horizontal paper. So use always paper on a landscape mode horizontally. So you can draw a line and you can name it as a principal axis. So this is principal axis. Then exactly at the midpoint of this line, identify a point and name it as pole. For any lens, it may be concave lens or convex lens. So these logics only we will follow throughout the ray diagrams. So first thing, drawing the line horizontally, then identifying a point exactly at the middle, then name it as pole. Then draw a perpendicular line passing through this to identify as a lens, that line as a lens. So double convex lens now I am drawing. So double convex lens is drawn. That symbolically. Next, identifying the focal points and center of curvatures. So morning I give you one logic. From the pole, focal points F1 and F2 at equal distances. Center of curvatures also at equal distances. And one more logic we will follow. Here focal length is double to the radius of curvature. So here pole to the focus. Suppose if you are taken 4 centimeters gap, then focus to the center also, I'll use that same 4 centimeters gap. So that logic will give you without any memory about the ray diagram's characteristics. So no need to remember them. Directly we will get the characteristics. So identifying the focal points exactly at a 4 centimeter distance or 5 centimeter distance, it depends on the paper length. So you can reduce it by your choice. But equal distances logic you must follow. Then center of curvatures from the focus, right? So pole to focus, what the gap you are maintain. Focus to the center also same gap you have to maintain. Right? So PF1 distance always equal to F1 to C1 distance. PF2 distance always equal to F2 C2 distance. So that logic I am giving you. So this is we are following. So this logic you have to follow and also practice in your ray diagrams. Then next, here simply object we are going to place. But in case of infinity, as we learned in the reflection chapter, when an object is placed very far from lens or the mirror, we will get the parallel light rays. So in this case, object is said to be at infinity. So at infinity distance, right? That means object is placed away from lens and it is beyond the center of curvature very, very far. That we will get parallel beam of light rays only. So when the object is at infinity, no representation of object. So we will consider only parallel beam of light rays. So here, look at any ray. Suppose this first one I am considering as R1 here. So how this R1 to the principal axis? So this is your principal axis. So how it is to the principal axis? Parallel. So when a light ray parallel to the principal axis, it meets the situation 1. So here, situation number 3. So in the situations we have learned, when a ray parallel to the principal axis, after refraction, or you learned this already in the figure number 8, when parallel beam of light ray incident 8 ABCD in your textbook. So look at that diagram once. When a parallel beam of light ray incident, that after refraction passes through the focus. After refraction, it passes through the focus. So simply we can draw the refracted light rays that which are passing through the focus. So one after the other I am showing you very clearly. So each ray after refraction passes through the focus. So all the light rays traced here. So now find out the converging point of that light rays. So where is the converging point of light rays here? Simply that is observed at F1. This is point of image. So you will obtain a sharp image when you put the screen exactly at the focus F1. So this is F1. Then here we have to identify the characteristics. Note down that characteristics by observing. So here simply for the characteristics of the image, I will give you one code. You never forget it, right? So code for writing the characteristics of the image. That simply I will give you TDSP as a Telangana DSP, right? So TDSP. So using that code, you are able to write the characteristics. How, sir? So I'm using each letter for each character. TDSP. So 4 letters to write the 4 characteristics. So first T. So what T tells us? Type of the image. It is real or virtual. Real or virtual. So real or virtual also easily you can identify. Real image. That is by the converging rays. If the image is formed by actual converging of light rays, that is real image. If the image is obtained by backward light rays, then it is virtual. So real image by the converging of light rays directly without any backward light rays, then virtual image by the backward light rays. So here actually I obtained image by actual converging of light rays. So actual converging of light rays is observed exactly at the F1. So this image is real. This image is called real. Otherwise, we'll go backward light rays. That we can call it as virtual image. So that is first one, T. The next one is D. So what D tells us about the direction of image, facing direction of image. If the obtained image is faced above the principal axis, that is virtual image, erector. We can write is that code erector. So facing upward above the principal axis, we can use that symbol eyes to indicate. It is as erect image. So upward direction, erect image. Downward direction is inverted image. Downward direction is inverted image. So that logic we will follow here. Then after direction, one code is there. Yes. What is yes? About the size of the image. Size of the image. So size is greater than the object size. Image size is greater than the object size. We can use one code. Larger. Image is larger than object. Large. enlarged. If image is smaller, diminished. So diminished or enlarged code we can use as for size. Then one more code is there, P, position of the image. So where you obtain that we can see that, right? So these are the codes I am given. To remember that code size, one abbreviation I am using here, TDSP. I am using here TDSP. So simple code will be given to remember the characteristics. So by following that code, I am writing the characteristics here. T, type of image. So obtained by actual converging of light rays. So we can use it as real. We can write it real. So first one is real. The next one, maybe direction or the size, whatever it may be, you can follow the order. Suppose here size. Size is mentioned upward or downward, above or below. So you are unable to find the direction, above or below. Exactly, it is on the principal axis. So we cannot comment about the size. It is as point size. And you cannot say it is erect or inverted. So direction is not obtained. So I cannot comment anything about the direction, either erect or inverted, because it is a point, not above the principal axis, not below the principal axis, only a point, no size for the point. So no comment about it. Then its size is point size. And position, exactly at F1, at focus. So these are the characteristics, right? Then we will go for the next position. Next position is, I'm coming from infinity distance. So beyond the center, that is beyond C2. Object we are representing beyond C2. So here beyond C2, representing the object. So for that also, I'll give you one simple logic for obtaining the image at very easy concept. So that is simple. First, horizontally, you can draw a line called the principal axis. Then exactly locate its midpoint. Then draw the convex lens symbol. Okay, drawn. Then eyes I mentioned in the first one. Use the same logic. 4 centimeters or 5 centimeters gap between each points. Any 2 points, 5 centimeters gap or 4 centimeters gap, depending on the paper width. So F1 and F2 from the pole, same gap, 5 centimeters left side, 5 centimeters right side. From the focal points, centers we can identify. Exactly same gap as you maintained between P and F1 or P and F2 gap. So 5, 5. So exactly F1 to C1 or F2 to C2, 5 centimeters again. So between any 2 points, fixed length, that is the logic. Then object. So where is the object? Beyond the center of curvature. Always object is represented by arrow, that is above the principal axis. So for that, I'll give you one logic here. That is exactly width of the scale. Where is beyond the center? So always object is placed left side. So that center is C2. Left side center is C2. Don't get confusion, as I explained at the beginning of this video, right? So object is placed exactly equal to the width of the scale. So for drawing also, object drawing also with this logic. So I placed simply my scale above the principal axis, which is coincides with the principal axis and above. So as you see on the screen, then draw the object beyond the center and equal to the width of the scale. So this is object for us. Then selecting 2 rays. Already I mentioned which rays they are. One is parallel to the principal axis and the other ray passing through the optic center. One is parallel to the principal axis and the other is passing through the optic center. Only 2 rays throughout the ray diagrams will follow because generalized behavior. Okay, so every situation they are possible. Then here simply drawing the parallel light ray without removing the scale as I placed it previously. So following that, width of the scale, easy to draw the Parallel light ray. So light ray is drawn onto the principal axis. Now, onto the convex lens. Now you can remove the scale. That's it. Then second ray. Second ray is passing through optic center. So just join the top of the object and the pole. So always use long scale. Don't use the small scales, 15 centimeter, 30 centimeter long scale. So join top of the object and the optic center as you see. So joined. Then draw the light ray, that which meets the pole. So we know the behavior of this light ray. Don't remove the scale. So as you placed, continue. Why? Because the light ray behavior is fixed. Light ray behavior is fixed. That is what? Simply it remains undeviate, passes in the same direction through the lens. So you can trace that. Completed. So this is the logic. Then remove your scale. So one ray already completed. Then what about the first ray parallel to the principal axis after refraction? It passes through the focus. So instant point, this point is instant point. So join the instant point and the focus using the long scale. Then draw the refracted light ray, because ray which is parallel to the principal axis, after refracting from the convex lens, it passes through the focus. So simply I can draw a line that identifying as a refracted light ray. So the direction also given as arrowhead. So remove your scale now. Then look at that light rays are converging themselves or not. That light rays are actually converging at a spot, this one. So this is image point. This is what? Image point. So we can draw a perpendicular from this onto the principal axis. From this point to the principal axis, indicating direction from the principal axis. So it is below. So that's why I'm using arrow direction below the principal axis. Arrow directing below the principal axis. Right? So this is the logic. So easy to obtain the characteristics of the image using the code. So image already obtained. Where is image? Between F1 and C1. The downward arrow. So here you have the image now. Then look at the characteristics. Look at the characteristics. Just a second. Okay, sorry for interruption, emergency call. Okay, so I obtained the image. Now we have to write the characteristics of the image when the object is placed beyond the center of curvature. So I am following the same code. What is given? T, D, S, P. T, D, D, S, P. So T is type, D is direction from the principal axis, above or below. Right? Next, S is size, P is position, TDSP. So now I am following type. So what is first one is real, because I obtained by actual converging of light rays at this place. Image is real. Image is real because directly they are converging at this place. The next, downward. It is downward. Direction is below the principal axis. So what we can write? Inverted image. Direction above the principal axis, erect image. Otherwise, inverted image, downward. Then size. What is size? What is size? Here compare or measure with the scale. So here simply I will use a line to measure here. Exactly equal to. Right? So I'm using a box here for indicating the size of the object here. So I'll give you clarification to you. Right? So this is the size of the object. Then I'll move this towards the image. I'll move this towards the image ISTs. So without changing that. So now measuring how it is smaller. Image is smaller. So simply what we can write, if it is smaller, larger means enlarged, smaller means diminished. So we can write the size of the image as diminished. Then what about the position? It is observed between F1 and C1. Between F1 and C1. So the position is between F1 and C1. So I think it is very clear. Characteristics, how to write. Give me your comment, please. You have option to comment. So give me your comment. Okay. Then we'll go for another position. So next position is simply here. Next position is simply here. About the place of the object is center of curvature. Exactly, it is placed at center of a curvature. If you are in confusion, please give me your live comment. I am following the comments also. So immediately I will give you answer for your question. Okay. So here simply, now object is placed at the center of curvature. Object is placed at the center of a curvature. What happens? What are the characteristics of the image obtained when the object is placed at center of curvature? So for that also we will follow the same logics. Now I am using only the explanation, no scale. So same logic you can imagine. So horizontally one line drawn, that is called the principal axis. The next here, simply perpendicular drawing at the midpoint identified as pole. So that line making as a convex lens. So drawn. The next identifying that points at equal distances from the pole. So focal points at 5 centimeter distance. Then center of curvature from the pole 10 centimeters. From the focus is 5 centimeters. Don't get any confusion. From the pole 10 centimeters. From the focus 5 centimeters. Right? So F exactly middle between P and C2. Exactly at midpoint. F2 or F1. So don't get any confusion. If there is any confusion, just message me. Okay. Now object exactly width of the scale at center of curvature. The next, you placing the scale ISTs. Placing the scale ISTs. Draw the parallel light ray from the top of the object. Okay, light ray is drawn onto the convex lens. Then next one, drawing the light ray towards the pole. So I am completing that. So when a parallel ray is incident on a double convex lens, so after refraction it passes through focus. So that is completed. Then second ray through the optic center. So through the optic center, that light ray remains undeviate. That light ray remains undeviate. So extend it ISTs. So here I got the point, converging point. So this is converging point directly obtained, not backward light rays. So directly they are converging after refraction. So that we can consider as image point. So from there you can draw a perpendicular onto the center. Then automatically you will obtain the image below the principal axis. So arrow direction is given downward. Arrow direction is given downward. Next, writing the characteristics using the code TDSP. For the image, I am using the code TDSP. So T is type of the image. So actual converging of light rays forming the image is called real image. Then D, direction. The direction is below the principal axis. So exactly oppositely faced to the object. Object upward. Image is downward. So inverted image. Direction is inverted. The next here, simply we will go for size. TDS. S, size. So size is compare. So I will show you that. So using here simply a box. So here is a box is considered. Then the box I am moving ISTs towards the image. So exactly they are same in size. So the size is measured and observed as same size. Size is same. Then what about last one, position? So where is the position? At center, right? So one more I said. So you are maintaining here equal gaps. So that's why what I can write here, exactly at same distance at center. So at C1, at same distance at C1. Object is at C2, but image at C1. Okay, not at same place, at C1. At same distance, but another side of the lens. So like this, you can comment about the characteristics of the image. So this is very easy to draw. And one more, sometimes you may get at various positions, so you can manage in your examination. If you are not obtaining, just you have to manage, right, to give that image exactly at C1. Don't forget it. Okay, then fourth position is object placed between center of curvature and the focal point. So now same procedure we are following. Horizontal line drawn on the paper, then midpoint is recognized as pole, then drawing the perpendicular and making as a symbol of convex lens. Next, identifying the focal points at equal distances from the pole and identifying the center of curvature at equal distances from the focal points. Same distances, 5 centimeters. Then placing the object in between C2 and F2. So object is drawn equal to the width of the scale. Then using the width, drawing the parallel line, parallel to the principal axis from the top of the object. Then we know that refracted light ray passes through focus after refraction. So extend it as much as. Then second ray from the top of the object towards the pole. Then extend it. So extend as you get converging point. To get a converging point. So I obtained a converging point. So that point is what? Image. So draw a perpendicular onto the principal axis. This is also downward. So using the characteristics code TDSP. So image is obtained, characteristics writing using the code type actual converging light rays. So that is real image. Next, direction below the principal axis, inverted image. Next, size. Size is enlarged. So already larger image than the object. Image is larger than the object. So enlarged, large, enlarged. Then also you can use word magnified. Instead of enlarged, we can also write magnified. Then finally, position. It is beyond C1. Location also given, C1, beyond the C1. Then fifth position. That is exactly at a focus. Exactly at a focal point. Sorry, this animation actually not there. Okay, I'll explain you. Simply, I'll draw principal axis, then identify the midpoint as pole, then drawing the symbol of a lens, then identifying the focal points as F1 and F2. Next here, center of curvature, C1 and C2. Next, object is placed exactly at F2. Then following the same logic, parallel to the principal axis from the top of the object. Okay, drawn. Then after refraction, it passes through focus, extend it. Then one more light ray from the top of the object, then extend it. After refraction, it remains undeviated. So how they are? For any extension, they never meet. So that's why you are drawing a line backward from the point of instance. So I'm using here a green color for this. Okay, so now you can look at that, extending in the backward direction. So this is. Then from here, two light rays are extended in the backward direction. Do you see any point commonly obtained here? No. Then measure the gap between these 2 points. So that gap almost remains same. So I'm moving this one from one place to the another place. So that gap almost remains same at any point. So that's why here we can comment about characteristics of the image obtained in this situation. Characteristics are here given as real image only we can give it as. Then size highly enlarged or no comment, blank, right? So inverted and highly enlarged. Then position is at infinity because you are unable to reach the point because they are moving parallel. So these are the characteristics, but in your textbook, they are given as real image, okay, and infinity, okay. These are no comment, blanks given, okay. So anything, it is actually available in the CBSE book. That is, I said. The next here, simply we will go for the last possible position is object between focal point and the optic center. Then in this case, that object is exactly placing between pole and the focus. So same logics will follow. Object is represented. So object placed between P and F2. Then from the top of the object, two light rays needed. One is parallel to the principal axis and the other is passing through optic center. So draw the refracted light rays. So for any extension, they never meet, but the gap is increasing. So these light rays are appeared as diverging light rays. So in this case, we can draw the backward light rays for them. Backward light rays. So there you can draw a perpendicular onto the principal axis. So that is considered to be image here. So this is the image. This is the image. So what are the characteristics of image? T, type, virtual image, because with the backward light rays, the image is obtained. Then facing direction is upward, same as like your object. Then it is said to be virtual, right? And direct. So virtual, erect, then size compared, image is enlarged, large, enlarged, then magnified word is used. Finally, position beyond F2 on the lens only, right? So virtual image is observed on the surface of the lens, So simple it is. Then we'll go for another. What is concave lens ray diagrams? So I'll explain you only one diagram. That is here. Okay. So before going that, one more topic I forgot. We are generalizing the characteristics of the image in a table, right? By observing the all ray diagrams at a time. So from that, we are simply writing the position of the object, and position of the image. Then it is a real image or virtual image. Then diminished or enlarged. That characteristics we can note down. So what are the objects, places we used? Simply, I used object is at infinity. So when the object is at infinity, position is at focus. So that is on the focal point F1. Then object placed at at infinity, and the image is focal point. Characteristics are written simply point image. Then no comment about its direction and another size. Size. Okay. So these only we can write. The next one I am giving you at F2. Why? Because here when the object is at infinity, image at focus. When the object at focus, image will be at infinity. So that's why I am giving you this one. So easy to remember. So object placed at F2, image is obtained infinity. How we decided? Because that refracted light rays are parallel to each other. Then characteristics are written as blank as per your textbook. But in another textbook, I observed highly enlarged and inverted. So that's why in the characteristics I wrote that. Then at infinity, focal point, at focal point and infinity. So this is the relation. Then beyond the center of curvature, beyond C2, image is obtained between F1 and C1. Then characteristics diminished, inverted, real. So by drawing, you can generalize that. Then next, we'll go for between F2 and C2. When the object is at between and C2, between F2 and C2, then image is obtained beyond C1. So look at it. Beyond, between beyond. So that logic I am following you to remember, right? Memorizing that easily with this at infinity, at focus, at infinity, beyond, between, beyond, right? So that is the logic. So characteristics enlarged, inverted, real. So enlarged also expressed as magnified. Then what are the remaining? At infinity, completed, beyond, completed, exactly at center of curvature, C2. We observed at C1. Then characteristics, same size, inverted, real. Then what is remaining? Between P and F2. So in this only one case, we have observed that image is virtual. The remaining all are same. All cases real image is obtained, but only one case virtual image, that is erect. Virtual erect. Only in one case. So these are the logics for the table. So then next we'll go for image characteristics for the concave lens. So ray diagrams. So in this case, just I will show you in the animation only, no explanation. So all the points identified as we discussed. At infinity, no representing of object, just parallel beam of light rays. After refraction, they appear to diverge as we learned in the figure number 8, A, B, C, D. So they are all diverged. So in the backward rays, we will obtain that characteristics, right? The image is exactly at F1. So like this, you can obtain the image in case of the object at infinity. Then characteristics, same TDSP. Virtual, because backward light rays giving the image, then it is said to be erect, but no comment as per our textbook, right? So you don't write anything. Next here, we'll go for another. T, D, S, size, point size, P, position, exactly at focus. So these are the characteristics we can write for that first position. Second position is at beyond the center of curvature. We are moving away from the lens, towards the lens, right? Away to towards. So beyond. So what are the characteristics you will obtain? Object represented beyond the center 1, C1. So parallel to the principal axis, and one more ray is appear to diverge from the focus. One more ray is through optic center. So without any deviation, it passes. Without any deviation, it passes. Now in this case, you will obtain the image where that two light rays coincides each other. One is backward light ray and the other is refracted light ray. So directly they are obtained. So there you can draw the image. Then characteristics of the image. So image characteristics are written virtual because diverging light rays are giving. Then size, facing direction upward, same like object. So erect. Then diminished, size is smaller, object only large, image is smaller, so diminished. Then position between F1 and P, pole and focus. So these are. Then next we'll go for other positions, but no explanation, just observe. So here object is placed beyond the center of curvature, same logics following. Then here object representation using the width, then parallel to the principal axis. It is appear to diverge, so you can complete that. Then one more ray without any deviation, so you obtained again same characteristics, no change. Object position changed, but characteristics of the image formed by the concave lens not changed. Then next position, in this also you will observe the same thing. Object position is changed, but remains characteristics of the image same, no change. Next, object position changing. So what happens? In this case also you will remain with the same characteristics of the image. See, same characteristics obtained. Then next, last position is between focus and optic center. So in this case also you will obtain the same thing. Never change. Its characteristics always remains same. For all the positions, for a concave lens, I obtained virtually erected diminished between pole and focus. Only in one case, we cannot comment about the direction and size of that only direction. Remaining we can write virtual diminished, that is point size. Okay, that's why you are able to say diminished point size. Then between pole and focus, these are not changed. All are remain same only. No change in the characteristics. So that's why I didn't discuss about the ray diagrams clearly. So simple. If you know one thing, all characteristics are same, but drawing is differently. Okay. Then we'll go for the next topic is about the special situation. This is very, very interesting actually. And majority students are confusing in this topic only. So what is special situation? That simply parallel beam of light ray, but making angle with the principal axis. So there are problems, right? What happens when parallel light rays are fall on a convex lens? Already morning explained, just for simple understanding, I will show you once again here. Parallel beam of light rays making angle with the principal axis. Right? Light rays only parallel, but they are not parallel to the principal axis. Right? So simple, extend that light ray which is passing through optic center without any deviation. Then draw a perpendicular to the principal axis through F1. Through F1 for any lens, through F1. Perpendicular is drawn through F1. Okay, drawn. Then I will obtain a common point that is identified as imaginary focus. Imaginary focus. So I got imaginary focus. Then connecting all the refracted light rays at that point only. So converging. Convex lens, converging light rays. But that converging point not at F1, at imaginary focus. Right? So this is. So already I shown practically what they observed. That is only given as diagram. So always that a parallel beam of light ray passing through the convex lens after refraction, converging at a point that is lying on the focal plane, but not at exactly principal focus. So F1 is principal focus. Any point you can select on the focal plane called imaginary focus, secondary. Okay, so this one. So this is the special situation for the double convex lens. Now concave lens, same thing. Parallel beam of light rays, but making angle with the principal axis. So what happens after refraction? They seem to be emanate from the focus only, but that focus will be not F1, will be on the focal plane. So what is focal plane? That is drawn from the F1 only. So one ray remains undeviate. Okay, completed. That simply assumed as the principal axis, imaginary principal axis. So now draw the focal plane from F1. Then identify a point that undeviated light ray and the focal plane where they can coincide. That point is imaginary focus for you. Then connect all the light rays incident on the lens that points with the focal, for imaginary focal point. So that red color spot is given. Then connect all the incident light rays with that point, with the dotted lines. Then extend that dotted line as a ray after the refraction. So as you see here, green colored light rays. So this logic we are using in all the problems, example 5 and example 4. Okay, now look at that practically what they have observed. Parallel beam of light ray, but making angle with the principal axis. So after refraction from the lens, that diverging point always remaining on the focal plane. So this you have to remember. So that orientation we have to see in our mind when you get a ray diagram problem. Right? So what are the problems here? That we'll look at now. So this is given as example 4. So what is actually? Draw a ray diagram to locate the position of image when a point source is placed on a optical axis MN of a convex lens. So as you see in the figure, so I will show you that figure is given in your textbook in such a way that is beyond the focal point. So that question figure I will show you here. So simply that object is placed on the optical axis MN beyond the focus. So F2. Then that green color spot is object given as source S, right? So that is, so in this case, I will consider two rays. One is from the O making angle with the principal axis. Making angle with the principal axis. And the other is along the principal axis, no representation. So here the light ray which is making angle with the principal axis is going to meet lens at a point P dash. At a point P dash on the lens. Then what to do in this case? What to do in this case? So simple, we will make it a special situation, this one. So how do we? How do we? Just we have to draw a parallel line to the given light ray. Parallel line to the given light ray. Right? That parallel line, especially through the optic center. Right? So here one ray is considered from the source that is along the principal axis that can move continuously without any deviation. But the problem is with this light ray. Suppose it is giving you as R1. So R1 does not match with any situation 1, 2, 3, 4. Okay, so in this case, we'll go for the special situation, special case, right? So what to do in this? In this case, we'll simply drawing a parallel line through the optic center. So red color line, right? So red color line is drawn. Then what to do? Imaginary principal axis. Red color line is what? Imaginary principal axis. Then the light ray is parallel to the principal axis before the refraction. Only you have to consider in this case red color line only because does not match to the any situation. So special situation. So imaginary principal axis is taken. That is parallel to the given light ray. Then draw the focal plane. So drawing the focal plane through F1, not F2, through F1 for any lens. So draw a dotted line. Then identify a point where they can coincide each other. Imaginary principal axis and the focal plane. That we will take it as imaginary focal point. That is F0 is given here. So that black color spot is F0. Then what to do? After refraction, so a ray is parallel to the principal axis that passes through focus. So imagined parallel to the imaginary principal axis. Then the light ray also imagined passes through the imagined focus. So extend it. So this is extend. They can meet at a common point. What? The two light rays which are considered. Suppose here this is R1, this is R2. R1 and R2 after refraction, they are going to meet at a point. So that point is image point for you. So that image is obtained at I. So this is example number 4. This is example number 4. Very easy one. But small confusion, right? So we will avoid that confusion by following the example 5 here. So simple example 5 to solve that ray diagram problem, right? So they will give you only one ray. You have to make it as parallel beam of light rays. So I will show you in this. That which match with the special situation. Okay. So here complete the ray diagrams to show the paths of the rays after refraction through the lenses shown in the figure E5A and E5B. E5A and E5B. So how do we? So look at that. That figures are given E5A and E5B. in your textbook like this. Then I'll draw that on my paper, right? Copying the same diagram on my paper. So draw it. So simple, draw the lens, draw the principal axis, then identify their focal point size f1 and f2 respectively given in your diagram, then draw the same light ray as given in your question figure. Then what to do? So here special situation, you have to make it as special situation. How do we? Simple, parallel beam of light ray making angle with the principal axis. So I will draw the parallel light ray for this one. Look at, so I drawn a ray on the same line because it is animation. So that's why I am unable to draw parallel light ray. So that light ray with the same angle, I'll move it down. So very easy for me. It is parallel. So that is simply from the bottom. Okay. Then one more ray I will draw. One more ray I will draw. So one more I am drawing here. Exactly parallel again. So on that I am drawn. Then I am moving this with the same angle parallel. So all these light rays are going to meet where? On a focal plane, right? So how we can identify that point on the focal plane? Just simply drawing a parallel line through the optic center. For this, draw a parallel line through the optic center. So look at that. I am drawing the parallel line to the given light ray. Then remove your scale. Now draw the focal plane. Focal plane is drawn. Then identify the imaginary focus on the focal plane. So which is imaginary focus? That is black colored spot. Coincides each other. The line passing through the optic center, imaginary line, then perpendicular is drawn called focal plane. They can coincide each other. That point is imaginary focus. Identifying as F0. Then what to do? After refraction, that light ray passes through. Just it. So now look at the remaining light rays. How many are given? The same logic. All the light rays are going to be converged at a focal point. So simply you can draw the refracted light rays for all the given light rays here. Passes through. From that, passes through. So look at that special situation is obtained. Very easy one. What to do? Drawing the parallel line is important. But condition. The light ray is given before refraction or after refraction. That is very, very important. Right? So this is the trick. Okay, then we'll go for concave lens. So for the concave lens, as given in your question figure E5B, copying the same diagram. Then the object is, light ray is given below the principal axis onto the concave lens. What to do? So before refraction is given, so I will follow the same logic, passing through. A line passing through, but parallel to the given light ray. So put your scale. So before only I am drawing the focal plane at F1. Then drawing the parallel line. So they are coincides each other. They are coincides each other. Then that point we are taking as imaginary focus F0. If you are very clear with this, then the problem is very easy. If you are in confusion how to draw that line, then it is difficult. Definitely you will do the mistake. Definitely you will do the mistakes. So don't get any confusion. Understand, parallel line ray for the incident light ray. Incident light ray, not for the refracted light ray. Then join the point of incidence and the F0. Simple. Dotted lines. Then this is the diverging light ray. You can draw the diverging light ray. This is the trick. Easy one. So put your comment please immediately. If you are in confusion, I'll explain again. Otherwise, we'll go for another. Please do it immediately. Are you very clear? Right. Shivani given comment. Shivani given comment. So everyone is clear. Okay. Now we'll go for another. So everyone may be clear. No comments. We'll go for another. So here that example is very clear. Now here I am going for the lab activity to observe the type of images and measuring the object distance, image distance from the lens. Object distance and image distance from the lens. So what is the lens is we are selecting? That is double convex lens. So what the ray diagrams are drawn, the same we will observe here, right? So for that required materials, I am taking a double convex lens. To place this, we required a stand called V stand. Next, I need a object. I is the object. I am using candle. I is the object. I am using candle. The next, I am using the tape for measuring the distances or a meter scale. Tape or meter scale, anything you can use. Then finally, we will need a screen paper, white sheet paper. These are the required materials. Then simply we'll go for lighting the candle and placing the object from the lens at various positions, then measuring the object distance and image distance, and writing the characteristics by observing the image. Right? So simply we'll go for precautions. What are the precautions here? So Sanjeev commented, in any lens or any incident ray, make an angle to lens, compulsory draw parallel line to the incident light ray through pole. So whatever it may be the lens type, any lens, if you got incident light ray, then you have to draw the parallel line that is passes through the optic center P. So I will show you here again. Simple. Look at this. Here in this case, you obtain incident light ray in the question figure. See here, incident light ray only given. For this, simple trick is parallelly you can draw a line that is through the optic center. Then only you will get imaginary focus through the plane. Right? So that is on the focal plane. See here. Right? So this is. Any confusion, Mr. Sanjeev? Parallel to the incident light ray compulsory. For only incident light ray, line passing through optic center, it is compulsory. Okay. So for any lens, I'll give you one more in our next class. That is highest difficulty level problem. Okay. That I will explain you. Don't worry about that. So in this lab activity, we are observing the object distance and image distance by taking all these required materials. Then what are the precautions here? So here simply we have to observe the image very clearly. How do we observe the image? Maybe on the screen or maybe on the lens surface. If it is a real image, that image will be observed on the screen. So here moving or placing the screen exactly at the sharp image. So adjust it. So that is the image. Then that is the precaution here. So always try to obtain the sharp image. Right? Then here we use a lens that is with the non-focal length. So select the double convex lens with non-focal length. Then here try to obtain the sharp image on the screen. Then measuring the distance as much as possible accurately, right? So without any parallax errors, so that don't do the mistakes. Then here simply we will go for noticing table. So what we can note down? Object distance, so image distance, and characteristics of the image also. So note down table, you can make it like this. Also we are able to calculate the focal length because we have a relation between the focal length, object distance, and image distance. So that we will derive a formula after this one. So what is the focal length also you can find out using that formula after derivation. So object distance we can note down, image distance we can note down, and finally focal length. Then from these observations you are able to generalize about the characteristics of the image. That characteristics of the images are always same or changes, right? So that is we can give the generalization. So I selected a long table. Then on the long table we are going to place the lens with V stand exactly in the middle, right? So either sides you need gap same equally. So at middle you have to place the lens. Then after placing the lens, measure the distance from the lens one side. So here I am going to place the object exactly at 60 centimeters distance from the lens. So that distance I shown on the screen. So object lighted candle you have to place at 0 of the scale. So 0 to 60, the gap maintained between object and the lens. Then just you have to take a precaution. Object flame must be above the principal axis. So just imaginary line I am showing you. That candle flame lying above the line. So above the principal axis. Then move your screen. Right? So note down the object distance first in the table. So noticed. Next, obtain the image. Obtain the image. So what to do? Move the screen another side of the lens. So take the screen. So screen is taken. Then move it slowly away from the lens. So the image is obtained on the screen. The image is obtained on the screen. So observe the characteristics of the image. So here it is enlarged or at same or inverted or erect, then position. So they are all we can comment by knowing the distance. So measure the image distance here. So exactly at same distance almost 60. It is at 60. So note down the image distance in the table. Then change the position of object. So now placing the object exactly at 50 centimeters from the lens. So now same thing, lying above the principal axis. Then note down the object distance 50 centimeters. Then move your screen another side of the lens. Then move the screen. So you obtain image where on the screen. Now observe the characteristics. Measure the image distance. So what is the image distance is observed here? 70 centimeters. So 75. It is beyond. This is 70 centimeters to spot outside. So 5. So 75 centimeters is observed. Then change the object position again. Change the object position. Place your same thing. Actually, we are not disturbing. So on the table, I adjusted. Then object now shifted to 40 centimeters. So 40 centimeter distance from the lens. 40 centimeter distance from the lens. Then note down the object distance in the table. Noticed. Then what to do? Move the screen. So image is obtained on the screen again. Then measure the distance. Put your scale and measure the distance. Almost it is 120. So note down that in the table. Noticed. Then change the position. So 40. Next 30. So object now placed at 30 centimeters from the lens. Then again, note down the value in the table. Move your screen slowly away from the lens. Then observe. No image. So again, I am trying to move away from the lens slowly. Do you find any image? No image. So in this case, try to observe the image on the surface of the lens lying at same side to the object. Right? Then you cannot find any image. So we can write that no image. So let us try to see the image may be formed on the surface of the lens, same side where the object kept. We kept the object left side. So observe from the same side on the surface of the lens. Do you find any image? No image. We cannot find the image here. So at infinity, we can write it as infinity because not on the screen, not on the surface of the lens. We are unable to see that image moving any distance. So that's why we can write it as infinity. Then change the position 20 centimeters from the lens. Now try to see that image on the surface of the lens or the on the surface of the screen. So move the screen first after noticing the value in your table. Then slowly move the screen away from the lens. No image. Then what to do? If there is no image on the screen, let us try to see the image may be formed on the surface of the lens, same side from the object. So try to observe that image we can see on the surface of the lens. So observe that image on. So that will be observed like this on the surface of the lens. Then you can measure that image distance using another method. So I am unable to show that here. So later on I will explain you with already what a ready-made video. Okay, so this is you are observing on the surface of the lens. So that distance also we are able to write, but I will give you as on lens, right? So this is you are able to move that 10 centimeters also. Same thing you will obtain. So these are we observed, right? So that is about the lab activity. So if there is any confusion, just give me your comments about the class and about your doubts. So don't forget to comment about the classes, right? Then we'll meet with the another class